that we see, these are experimental. They're experimental. Because they're experimental, because they're going to fluctuate. If I had you guys roll dice 270 more times, are you going to get that again?
No.
However, it's not likely. I like that. No, because it's not likely. The chance of replicating that exact result is essentially zero. Can happen, just probably won't happen. What are you going to get if you roll the dice 270 more times? Something probably similar to it, assuming these results aren't unusual. Now, based on what we just saw with our experiment, I wish I had stopped at 242. I should have stopped it. I was still busy futzing around with the stapler. Chances are we're going to get something similar, yeah? So the column that Nick was asking about, that P of X column, what's the P stand for? Probability. What you've been talking about for the past 6 weeks in your project, probabilities. What's the X?
The number of
Tips.
Whatever the variable refers to. Exactly. Now, theoretically, what should these probabilities be? They should be 1 in 6 over time, because these little goofy, these erratic behaviors are going to smooth out over time. We're going to come back to that and let it go for a couple thousand, couple 10,000s. These should all go to 1/6 theoretically. Now, Nick, you said it beautifully earlier. You said there are 6 outcomes, each of which is equally likely. Perfect. That's why I start this with dice and coins, and we move into more ugly things that can't be done that way. Well, because the idea is not everything that's probability can be analyzed as equally likely. But for example, you know there's a 1 in 5 chance of a tornado today, right? Because I could think of 5 weather events: tornado, hurricane, earthquake, volcanic eruption, bright blue skies. 5 outcomes. 1 in 5 chance of a volcanic eruption today. If you cross the street, there's a 50-50 chance you're hit by a car. Because you either are or you aren't. This is dumb, right? You don't say things like that because it's not right. There's not a 50-50 chance of getting hit by a car, unless you're randomly running through the street. Please don't do that. I like you all far too much. But see, not everything is equally likely. We'll measure them, I'm thinking we'll measure those on Tuesday. So for right now, let's deal with the equally likely results, the stuff I just gave you guys, the dice and the coins. And then we'll move to the uglier ones, the more realistic ones, once we have the theory kind of in hand. Now, what you just saw, I want to kind of define some stuff while we're letting this thing run out. This column, combined with this column, taken together is what's called a probability distribution. Probably one of the most important things in this class. The idea of a probability distribution. These things are freaking rad. You could do so much. I've got a whole bunch of quizzes planned for you guys on these topics. I keep finding more and more data sets. I found one I was going to bring to class, and it's kind of depressing. So I'm not going to bring that one. But I found some other good ones too, like looking at average ages of certain characteristics across whatever variable you're studying. So probability distributions. Probability, there we go.
It's a combination of those 2 columns?
It is. That's my favorite way of looking at it, is a combination of 2 columns. And you can also do it with equations, you can also do it with graphs. There's many ways to do it. This is the simplest and I think the most effective way, is looking at it as a 2-column t-table. You're already used to this. You've already done frequency distributions. It's exactly the same thing, except you replace the frequency with a probability. And the mathematics, identical. The mathematics is identical. Let's come back to it. Okay, so eventually the simplest form is this. The simplest form. And I want to caveat this with, these are discrete data points. Everything we're going to be looking at over today and Tuesday are discrete probability distributions, meaning we can count the results. 1, 2, 3, 4, heads, tails, heads, tails. We'll get into continuous ones in the last 2 weeks of the class, I promise. It's important, I have to do it. But I don't want to do that right now, because when you add the measurement quality to it, it's like, now I'm learning 2 things at once. Let's learn 1 thing at once. We can already count fairly effectively, except for me. We can all count pretty effectively. So let's just utilize that. So the simplest form, you end up with a 2-column table. So you have an X column, and you've got a P of X column. Now this X column takes on values. The values it takes on varies. It varies. These go from 1 to 6. It could go from 0 to 10. It depends on what you're counting. Depends on what you're counting. So these values, they vary. Nobody has problems with that. As soon as you get into the experiment, people know what the outcomes are going to be. Sometimes you can't start counting until 3. Sometimes you can't start counting until 2. Sometimes you can't start counting from 1. Sometimes you start counting in negatives. Not very often, but sometimes you can. So this column gives you the probabilities of those values. So all of these columns have names. The x column, I spelled that wrong, there's an extra letter. It was like cumin and column all at the same time. The x column, we fill that with what are called random variables. Fill that with the random variable values of the experiment. And the experiment. Random variable. Another fun word from statistics. Random variable. Random variable. It's one of my favorite names in mathematics because those two words are so perfect together. Why is it called a random variable?
Because it changes?
It changes randomly. Good.
Independent variable?
Good. Those results that we list, now we only have one so far. We'll look at more today and more on Tuesday and more for the next 4 weeks. Not to make you dread the next 4 weeks, but you've got these values, 1 to 6. You know the range that they can take on. We figured that out right away, right? 1, 2, 3, 4, 5, and 6. We know the values. So there is a constraint as far as how big and how small. But we don't know which one's going to come up each time. How many of you have ever heard of somebody sitting in a casino waiting for a certain machine? Waiting for the little old lady to get up so they can jump on that machine because that machine is due, it's hot. It's either hot or it's due. I've heard both. I've heard it's hot, it's paying out all the time. Like, paying all the time? Interesting. And I also heard it's due. They've been sitting there all night pulling out one armband and it's not paying out. It's due. Over time? Yes, it's due. Define time, right? Define time. You've heard you've seen the movie Casino, maybe?
Yes.
The casino. Remember the scene? There's a scene in Casino. Actually, I'll come back to that. Let me come back to that. The overtime thing. It's Joe's point ad nauseum. But it's a good point. No, it's a good point. It needs to be repeated as frequently as possible. We'll come back to it. So anyway, the point of random variables is you know what can happen. You just don't know what's going to happen on any given trial. Just like you know when you pull the one-arm bandit in a casino, you know what the possibilities are. You want the 3 cherries or whatever the hell it is nowadays, right? You want those because that's a jackpot. But you also know the other possibilities, 2 cherries and a pineapple, or a cherry, a pineapple, and a pig nose, or whatever the hell they are. Whatever they are. Fair enough? Fair enough? Good. Okay. The probability column, the P of X column, that assigns likelihoods to each X. Please.
What's even better is the scratch-it tickets on the back. It shows 1 in 3.64. So you know which ones will show something winning more often. It might just be $1.
Every lottery that is played or gambled upon has odds given. You're going to analyze one. At the in-class quiz I've got, you're going to analyze a New York lottery system that screwed up and actually made it profitable to play the game for a very brief period of time. And 2 kids who had taken a stat class were smart enough to catch it. It's essentially the same game as Keno. We'll come to that, I'll get it on Tuesday. They made, well, you'll see it soon. Yes, any good lottery game tells you the odds of what you're playing on the ticket. It's usually in 3.5-point fonts, you can't read it, but it's there. And even if it's not there, you can figure it out based on the tools you're learning in this class. But usually they give them to you. And things like Powerball. Powerball, if the jackpot gets big enough, on average, each ticket you buy is actually making money on average over time. The trick is you have to buy so many of the tickets to see the average realize that it becomes bankrupting you in the process. That's called the gambler's ruin. Yes, if you can buy every possible ticket, you will aim with the jackpot and aim with the sub prize, and therefore you've brought in more money than you've put out. The problem is then the feds come and smack you with taxes, which negates any profit. But theoretically, theoretically, ignoring things like taxes, which
Don't the odds change with the number of people that buy the ticket?
No, the odds stay exactly the same. That's the interesting thing. What changes is the more people that buy the ticket, the more likely you're going to split the jackpot with somebody. So, in other words, that's what really buries you. How many times do you hear about Powerball jackpots with multiple winners? All the time, right? Because the big jackpots often have multiple winners. The little ones don't. The little 10 million and 20 million hits, nobody's buying tickets then. They wait until it gets to be about 600 million or so, 500 million, 600 million, and then everybody goes buys tickets. Which is interesting because right around that price point, is when the average value of a ticket goes positive and not negative. It's almost like human beings have an innate ability to process that. Like, oh, it's worth playing now. I mean, if for no other reason than you can't win if you can't play. Which I'm not saying is not, that's a perfectly fine reason to play.
But ultimately, you end up losing money whenever you gamble. Like go into a casino or play Powerball, you lose
Joe?
over time.
There we go. That's the whole point. That's the point of the movie Casino. Do you remember? Okay, we'll bring the scene up now. The Japanese businessman playing in the casino at De Niro's. What happened to him? They killed it, right?
He won it first.
He won it first, and what they tried to do?
They tried to get him to
Stay.
Well, they tried to leave.
Yeah.
Remember?
Well, they tried to leave, but they
No.
made him stay though.
Because that guy was smart enough to know that the probability of him going back, because they manipulated, like the plane broke or whatever, over time, that he was going to go back because, why? Because he liked to gamble.
They offered him free drinks.
Yeah.
Suppose, yeah, this is beautiful. Suppose, for example, this was the distribution of the gambling in that movie.
Right.
3 Japanese businessmen play, I forget how many, 3 or 4, how many, and they killed it. They killed, it was one guy. He killed it in the casino on the short term. So basically, he saw a bunch of twos, tried to cash his chips in, tried to leave. De Niro, oh, you're playing, you can't leave right now, you're playing, oh, sorry, the plane's grounded at the airport. Tell you what, take the greatest suite we have in the hotel, here's some more chips. Go keep playing. Go have a good time, keep playing. What happens?
He started losing them.
Over time, this starts balancing. You start losing because you have to lose. All those games are against you. You're going to start analyzing why in this class, why all those games are against you. Every Vegas game is against you. Even something as seemingly innocuous as craps, as you guys learned last term. Even craps has a tiny house edge. But that tiny house edge over time is all it takes to keep the lights on in Vegas all night and pump in water from LA.
That's why there's the 2 greens on
Not
the
this or
roulette.
anything. Yes! Yes! That's why you have green on the roulette wheel. To
Because
give you a slight house edge.
Yep.
Yes. Good.
Because black
Thank
and
you.
red would make it even.
With 50-50, but you put one green. English are even better than the Americans. English only have one green. American has 2. So English give you slightly better odds. Still crappy because you're losing on average, but you lose a little bit slower on average. Fair enough? We'll come back to all of this. You guys are hitting on lots of good points. But the whole point, the reason they can set those odds and essentially bank on making money on you is because they're analyzing this. They're analyzing this. Here's what I want you guys to do now. I want you to rerun the average of our experiment, but ignore that. Average it with the theoretical probabilities and see what happens. Average it with the, so change L2 is what I'm saying. Change L2 so it's all full of 1/6s. Rerun the probabilities.
Approximately 17%.
Good. It ends up being about 17%.
Okay.
Interesting you say that, Nick. Let's see how the old Excel is doing. Here we go, friends, just in case you're interested in how Excel is doing.
It's like
We're now at about 27,000 trials. 27,000 trials.
It's like not even.
There's definitely some rounding error. There's definitely some rounding error going on, but 45, 46, 45, 45, 44. Some of those are off by quite a bit, maybe 80 or 90, but it's 80 or 90 out of 27,500, which is not off at all, is it? It's not off at all.
Look at the pie chart. It's not.
And the pie chart is imperceptibly even. I mean, are imperceptibly different. It's perfectly even to our eyes. Of course, it's not perfect because these aren't exactly the same.
Right.
But we can't even perceive the offness. So, Carly, the Ziegler limit is kicking in. It's not 1/6, but is it close enough to 1/6 for argument? It sure appears to be. That's the whole idea. We're getting closer. We're going to keep going. We're going to keep going. We're going to add to that in a second. So, when you guys ran the, actually I'll turn this off. Turn the light on. When you guys ran the 1-var stats on your new distribution, your probability distribution, what's your average?